Okay.
Will I continue? No.
Okay. We're being recorded.
Am I recorded already?
Yeah. So, hi everybody, and welcome to this edition of the Motivic Geometry Seminar. Today we have Elden Elmanto, who his title is Motivic Topology and Purity for Torsors.
Right. Hi. So yeah, thanks for the invitation to speak, Paul and Glenn. So yeah, the title is Motivic Topology and Purity for Torsors, which is clearly a shout out to a paper called Topology and Purity for Torsors by Ben and Ben. And yeah, I'm very happy to speak about these things. And so this is joint work with Girish Kulkarni and Matthias Benz, both in Wuppertal. And yeah, so seeds of this, this kind of mathematics really, I really learned it from by diffusion from Ben, by some osmosis from Ben. And I remember we were in, me and Matthias were in this Mittag-Leffler seminar that Paul Arno organized. It was very nice, and we were talking about these things in this this Chinese restaurant, which was like one of the 3 things that you can go to eat to have lunch there. So yeah, it actually has like very old origins. But anyway, so I want to talk about what purity is, like this word purity for torsors. And this goes all the way back to work of Colliot-Thélène and Sansuc. So their setup is like this. So K is a base field, and G is a connected reductive group scheme over K, and X is an irreducible smooth K scheme. Okay. So the object of interest is this set H1 et al. XG. So this is a cohomology set, but it also has a concrete interpretation as the isomorphism classes of G-torsors, right? Where P is a G-torsor on X, and it's important that this is really etale, so I'm going to emphasize that. And the triviality that I request of these torsors is etale local triviality. Of course, up to isomorphism. And I want to regard this as a pointed set. Okay, so this, unless GM or some commutative group scheme, there's no group structure on this H1 etale. It's just has a structure of a pointed set. That's the only thing you can ever ask of such a guy. And yeah, so one of the things I learned from this project is that pointed sets are just way worse than groups. But anyway, yeah. So okay, so Colliot-Thélène and Sansuc asked the following question. So on the one hand, you can look at the image inside H1 et al. I should say K is this function field. Right. So I can look at H1 et al. KG, which admits a map from H1 et al. XG. Okay. So that's one thing I can look at. Another thing I can look at is look at the intersection, okay, inside X of X upper 1. So these are codimension 1 points in X. And I can look at the image of H1 et al. Or XX, right? So the local ring at little x. So G-torsors over those, and also inside H1 et al. KG. Okay. So how should I read this? So the left-hand side, or the top guy, a torsors on the function field. Okay, which extends to X. And the right-hand side are again torsors on the function field, which extends to codimension 1 points of X compatibly, say, because of this intersection. Okay, right. So you have some picture in mind. You have some surface or something like this, some surface, blah, and then like you have a bunch of codimension 1 points, which corresponds to some curves. Yeah, some curves like this, right? Okay, and yeah, so you can ask. So the torsor is like some dense open, and you can ask that it extends compatibly on this curves, but you can also ask that it extends to the whole of X. Right? Okay, so these are these are the two sets of interest, and there's a map from the left hand side to the right hand side, and we can check that this map is injective. And the question that Colliot-Thélène and Sansuc asked is question 6.4 of this paper that they wrote back in the even like 80s, I guess, of CTS. Is this map surjective? Or more accurately, you should really, instead of is this map surjective, you should ask when is this map surjective? As I will explain in a moment. Okay, so any questions before I sort of tell you what's known about the surjectivity of this map? Yeah, so this is also known as the purity problem for torsors. And yeah, so many people have like tried to understand this problem, and I will give sort of a sort of non-exhaustive survey on what's known and not known about this purity problem for torsors. So let me just start then. So 1. Okay. So if G is a special group in the sense of Serre, then this H1 cohomology set, H1 etale KG, is just a point, right? So G is like SL and SPs and whatnot, and all these groups that you like. Then so the result is trivially true, or rather purity is trivially true. Okay, so that's nothing to check, and these are the kind of groups that sort of has gotten all the attention in from the Motivic point of view, but the whole point is to look at other groups, right? This is one of the main points of the project, and Colliot-Thélène and Sansuc themselves proved that whenever G is a multiplicative type. So for example, tori, so gm to the n, right? This is okay. I'll say more about that later. And x, when x is low dimension, how low? Well, it's cool dimension. So smooth scheme of cool dimension less than equals to 2, aka surfaces, then this is okay for any reductive group. Okay, so this is already in their paper, and they of course ask the natural question, like to what extent is this phenomenon generic? Like you want to ask, for what group G, for what scheme X, does purity phenomenon or the purity map is surjective, right? Okay, so that's known in the 80s, and then later on in the 90s, so I'm gonna label this as local purity. Say X is the spec of O, where O is a regular local ring. And of course, because of my standing hypothesis, this is really containing a field. Right. Then in characteristic 0, Panin prove purity, local purity. Right, so what I mean by local purity is whenever X is replaced by the local analog, namely a regular local ring, for most classical groups. So by most, like you really mean most, so PGLN, ON, orthogonal groups, SON, special orthogonal groups, the spin groups, and things that, that Ben and Ben likes. So SLN mod mu D, D divides N. Okay, this kind of like sort of wannabe PGL. Okay, then also things like the special linear group of like an Azumaya algebra, things like this. Okay, so Panin proved that local purity is sort of a very unacceptable thing to think about, at least in characteristic 0. And Chernousov and Panin, so Chernousov and Panin proved local purity when G is this group called G2. If you ask me what G2 is, I wouldn't really be able to tell you, but Matthias seems to really like this group for some reason. Okay, so yeah, so okay, so that's sort of a characteristic 0 statement. It's like really like pretty beautiful geometry if you look at the papers. Then PGLN. So if I replace if I look at G to be PGLN, and I look at the subset of H1 etale blank P, I guess X, PGLN prime. So this is those Azumaya or like PGLN torsors. Whose Brouwer class have order prime to K, well, prime to the characteristic of K, right? So some reasonable subset, then local purity is also okay. And this is due to Ben and Ben, local purity is okay. Antieau Williams. In this paper, which motivated the title of this talk. Okay. Yeah. So the first non-trivial results beyond this multiplicative type or like low dimensional setup are all have to do with local settings, right? You want to ask purity not for like the entire scheme, but just as local counterparts. And let me write the 2.5, which is a tiny observation that we made that sort of kickstarted this project is the following. So and this will also be useful for setting up notation for the rest of the talk. So we set, as people do who study the Gerson conjecture, you put script H1 etale G, right, to be the Nisnevich sheafification of the pre-sheaf that sends U, the H1 etale. So this is non-script H1 etale UG. And I want to do this on smooth K. And it's a functor out of smooth, it's a pre-sheaf on smooth K schemes into pointed sets, right? Okay, so so this is the Nisnevich sheafification of this cohomology sets. Okay. Then you can show that if that H1 etale G has hence a local purity, if and only if, or rather, maybe this should be not script because it's hence a local. So this H1 etale G, right, that this cohomology set satisfies purity on a regular Hensel local ring, which is what I mean by Hensel local purity, if and only if it's unramified in the sense of Morel. If and only if this script H is unramified in the sense of Morel. So this is more of a comment to people who are, who are like deep into A1 homotopy theory. If this unramification doesn't really quite make sense, then the whole point of this comment was to just introduce this notation, the script notation. Okay, so you can show that the condition of being to have local purity with respect to regular Hansel local rings, right, is exactly the same thing as the sheafified cohomology sets, having purity in the sense of Morel. So that's maybe one way, if you are really into one homotopy theory, to think about this purity condition.
Sorry, Elden, whose result is this?
This is this is an observation we made, basically. You can try and prove it, Vofa. I bet you can.
Elden, can I ask another question? Does this include somehow Grothendieck-Serre's conjecture?
Yeah,
Okay.
I guess, yeah, you do need Grothendieck-Serre. Yeah, so okay, fine. So you call out my lie. Of course, this G is like all the things that that satisfies Grothendieck-Serre. But more on that later. Okay. Sorry. Yeah, I apologize. Okay. And in fact, what Grothendieck-Serre buys you is the following. So you can look at the image of H1 etale of R, G, okay, where R is a DVR, into H1 etale KG. This is in fact isomorphic to H1 etale G evaluated at R. And the injectivity part of this statement is exactly Grothendieck-Serre. And so this sheafified, so this is like, you know, if as R runs across all possible DVRs living in your like ring, if you, right, as R runs across all possible DVRs, that's the target of this purity map, right? The target of this purity map can be computed as just the sheafification of this H1 etale GR. Okay. Okay, so let me also give a bit of a digression on how to think about this a little bit more. So let's say I look at instead of you know, H1 etale XG, I look at something like H0 XOX. So just the ring. Let's say if I'm in the affine situation, then then if A is a normal Noetherian domain, right? So way more general than just smooth scheme over a field. Then I can write A as the intersection of all height 1 primes of A localized at P, right? And this is a algebraic Hartog's lemma. Yeah, which you can find in Hartog or something. I mean, yeah. So this is so you should think of this purity games as being somewhat analogous to, you know, some kind of Hartog condition, but maybe instead of like you know, extending functions, which is a map to A1, you're like sort of extending a map to stacks, right? Which is like will this be etale G's? Okay. And more is more. Okay, so that's kind of like, you know, some elementary thing. But more seriously, we can look at cases where instead of you have etale cohomology sets, you have etale cohomology groups. So you look at instead of H1 etale XG in general, we can look at, let's say, H2 etale XGM, you know, like a Brouwer group, like cohomological Brouwer group, which coincides with the usual Brouwer group of Azumani algebras modulo Morita equivalences in great general, right? Then the theorem, which I'm going to write and attribute to Hubler in the generality that we want, but also in the generality that I'm going to state, is due to Gaber and Sesnavicius. So what they showed is that H2 etale XGM is equal to the intersection of X inside X1 of H2 etale OXX GM. Okay. Inside, and all of this inject inside H2 etale KGM in this situation. So this is a purity for the Brouwer group. Right. right? And this is a very recent cool achievement of Kęstutis, but Hubler proved this in the generality of X being a smooth scheme over a field. And I think you probably need to look at the subgroup of those guys which are torsion, whose torsion is away from the characteristic. But yeah, so this is so you can think of this purity problem, this Colliot-Thélène and Sansuc purity problem, as sort of a non-abelian analog of this kind of purity for things like the Brouwer group. And what makes it sort of more pleasant to prove, I mean, it's not, of course, this is like a hard theorem, but what makes it sort of easier to digest, at least in my head, is that this is implied by a vanishing result that says whenever R is strictly Hensel local of dimension greater than or equals to 2, then you have this H2, then this is implied by a statement that says, if I take H2 etale spec R and then I puncture this local ring, right? So just extract out the maximum ideal with GM coefficients, then this is just 0. And so there's some kind of local to global spectral sequence argument that lets you prove this. Kęstutis in his paper wrote this like very neatly. So you're invited to look at that. But this kind of like local vanishing statement is somehow more digestible, probably in my head at least. And yeah, sorry. So this is for X being regular, Noetherian, integral, and regular. So super general, but in the generality we're interested in is just a result due to Ray Hubler. Yeah, but anyway, you can access this purity problem by just some kind of local computation from this kind of statement. So that's somewhat more digestible. Doesn't mean it's easier, but you have clear strategies on how to prove purity. Okay, so I hope at this point you sort of like, I work with groups all along. Why should I even look at pointed sets? Like pointed sets are awful. And in fact, it is awful in a very precise way. And this is part 4, and this is the work of Antieau and Williams, who gave counterexamples to purity. So this is the result. So when P is a prime and K is a complex numbers, and G is PGLP, then there exists affine smooth C schemes of dimension 2p plus 2, which witnesses failure of purity. Yeah. Okay. So from what these guys prove is that you should not expect purity to hold in a global setting, even though for the local situation is a reasonable thing to ask for. Right. And then the conjecture is that purity should fail for reductive groups over fields. Yeah. So the generic situation should be like the failure for purity, and you will want to furnish counterexamples. Yeah. So I mean, it's kind of sort of a funny conjecture, but yeah. So you want to furnish you want to produce counterexamples to purity. And the goal of this talk is to tell you a mechanism by which we can do this via A1 homotopy theory. But admittedly, we haven't produced new examples yet. Although we could use we see that the Antieau Williams technique recasted in A1 homotopy theoretic terms, do give us. I mean, it fits well with our machinery. That's what I wanted to say. Okay. Before I state the main theorem for the first time, any questions? No questions. Do you have any questions, Ben? All right. Yeah. So okay. So today, I'll state the main theorem. So I'll write this as theorem A. Okay. So let K be a field, and I wanna list a collection of fields or situations, rather, fields and groups where the main theorem holds. Okay. So when K is characteristic 0, G is a connected reductive group. Okay. So when K is characteristic to P, or characteristic P, G can be allowed to be PGLN, where N and P are coprime. Okay. And when K is characteristic not to ON, orthogonal group. And I also assume local purity is known for the main theorem to hold. Okay, so local purity from the survey above is known for a wide range of cases, right? So yeah, so the theorem is rather general. Okay, so that's the hypothesis, and I'm going to write a statement which could be a bit confusing, but I hope not. Then if purity for G holds for, well, then if purity holds, sorry, purity holds for, okay, so of course the statement depends on choosing a field, choosing a group, and a scheme X. Okay, so if the purity map is surjective for this in this situation, then the map from X B etale G in the A1 homotopy category into pi 0 A1 underline B etale G evaluated at X. So what is this? So this is the Nisnevich sheafification of the map that sends U into U B etale G, the A1 homotopy category, is surjective. And in particular, the failure of this map, the sheafification map from the A1 homotopy cluster maps into the sheafified version, if this map fails to be surjective, then you give counterexamples to purity. That's the point. And understanding this question is slightly more refined. I mean, there's like more. You can explain the failure of purity in a more reasonable way if you attempt to understand this map. And I'm going to explain that in a moment, but let me just put the theorem there for a bit. Any questions about this? Okay.
What about the converse?
Ah, yes. So remark. Okay. So remark. So even if purity fails, it does not mean that well, it doesn't apply surjective. Okay, I don't know. This is like really bad notation. It doesn't imply surjective. So the converse is not necessarily true, even though we don't have like an explicit counterexample yet. It's not.
You mean not surjective?
Not surjective. Sorry, logic is very hard. Not surjective. Okay, but okay. So, but let me argue why this is like a nice formulation of the purity problem. Okay. So to understand the map, okay, maybe we call this map something. Let's call this map Ken, because everyone likes to call things Ken. Canonical map. Yeah. Yes. Yeah. Yes, Chuck. So B at G is as in Morel Voivodsky's geometric classifying space. So maybe I should have clarified that. So this B at G is, you can think of this as BGMG in Morel-Voivodsky Totaro notation. Yeah, in the sense of Morel-Voivodsky Totaro, but you can also take this as, you take the classifying stack of G, you restrict it on smooth case schemes, and take the A1 homotopy type, or like the Motivic localization. Yeah. Yeah, so this is this is not like as opposed to something like B nis G, which has like, garnered more attention in the A1 homotopy community more recently, right? But yeah, so that's an important point. Thank you for making me say that. So let me say why this can map is like a nice reformulation. Okay, so so suppose I take alpha is inside pi 0 A1, the sheaf of connected components. This is what this B etale G is. X, right? So let's say I fix a connected component. Okay, so and in fact, hopefully we'll get to a point where I can tell you what this connected component is. So we also made some computation for what it is, but so you pick a connected component. Then what you can do is you can look at the Postnikov Tower. Okay, so here's the terminal object in this A1 homotopy category, and there is a tower which interpolates between choosing this alpha and an element in the homotopy set, right? So let me just write down this tower. Maybe need more space. Okay, so again, there's this can map and X inside B etale G. So first I choose an alpha, which determines a map to like the terminal object, if you want. So now there's this tower called the Posnikov Tower.
Elden, sorry.
Yeah.
Why is the zero truncation the terminal object here?
I mean, it's not, right? But I only choose. Yeah. Okay. Maybe that's bad notation. I'm sorry, Dennis. Can I write the zero truncation? Are you okay with this?
Yes. No, because I mean, a map to the terminal object is no data. That was.
Yeah. I understand. Sorry. That's much better. Thank you. Yeah. So just a map to the zero truncation, right? Right. So alpha is a map to the zero truncation, and there's a 1 truncation, the 2 truncation, the 3 truncation, and so on. So then you have all these maps. So if I pick an alpha, then there is some obstruction to lifting the map here, and there's also an obstruction to lifting the map here, and so on. And the game is to compute is to ensure that these obstructions vanish, and then you can go to the next stage. So if they vanish, you can go to the next stage. You can also enumerate the number of lifts, and if all these obstructions vanish, then boom, you win. You go all the way up, and therefore you're in the image of the can map. And these obstructions.
And sorry, another question. Are you like having an implied LA1 on the column?
Absolutely, of course. Everywhere there's always an implied LA1. Yeah. Elmot. Can you? Yeah.
Sorry, Elmot.
Yeah. So obstructions live in cohomology groups. I guess sets or okay. Well, I guess groups actually. Yeah. So they live in cohomology groups, and you have these obstructions OJ alpha inside HI nis of X with a J minus 1 A1. B etale G, but now these A1 homotopy groups are pointed at alpha as opposed to, I don't know, there's no canonical choice of a base point, so you're really pointed somewhere, right? And there's also a little twist here, which, if you are into this Postnikov Tower stuff, you can be worried about. If not, you can just ignore. And these are obstructions to lift. So maybe let me just sort of demonstrate how this works quickly. So if you have a lift like this, let's say you have made this lift, right? So you made this lift, and there is a map here called the K invariant. Is this maybe the first K invariant into K pi 2 A1 B etale G pointed at alpha 3. And if your K invariant vanishes, only then can you make this lift. Right. So this composite all the way like this determines what I've written here as I guess O3 alpha. So instead of like asking for a map to be surjective, I've broken it down into like a bunch of pieces. I've broken it down into a collection of obstructions. And if any of this obstruction is non-zero, you found a counterexample to purity. Of course, finding an actual counterexample is not that easy, but at least you can divide it into steps. And I think this is the value of this perspective. Any questions about this game? Okay, so I want to sort of tell you how we stumbled upon this theorem, and also tell you about how to a way to prove a sketch proof of this result. Okay. So back in the day, I was super into Asok-Fazel classification of vector bundles. So this is Asok-Fazel program. Which classifies vector bundles. I mean, classifies or say something about vector bundles on smooth, affine K schemes. Okay. So the beginning of this program starts with the following theorem. So X inside B, so I'll put in this here. So to contrast it with B at GLR in the A1 homotopy category. So this is maps from a smooth affine K scheme X, okay, into this B-ness GLR. It can be computed as actual vector bundles of rank R on X. This is actual algebraic vector bundles of rank R on X. So finally generated projective modules of rank R. And this is a result due to Morel at first, and then Asok-Koyawa events. I went on to take this idea and generalize it in like a series of 3 papers, which are really, really seminal in the subject, and give you mechanisms by which you can understand this isomorphism. Okay, so what you've done here is to place the algebraic classification of vector bundles on an smooth affine schemes purely in A1 homotopic terms, right? So just as in this is a precursor to the way that we phrase purity in A1 homotopic terms, and in the same way that you can understand purity via a collection of obstructions, you can understand vector bundles via a collection of obstructions, right? So you have a map from X into the zero truncation of B-ness GLR, and this time the truncation is just the terminal object. So you have no choice, right? So this is one of the ways in which if you put a B at here is very different from putting a B-ness, because in the B-ness world there's just no choice. The map is determined. In other words, this B-ness GLR is really A1 connected. And you have this various truncations, less than equals to 1, B-ness GLR, and you can play the Postnikov game, right? So to produce a vector bundle in A1 homotopic terms, you just have to eliminate a sequence of obstructions, and there's also an ability to enumerate the obstructions, right? So enumerate the lifts. So this obstruction groups lift here, and the lifts, the possible lifts, are enumerated by HJX pi j a1 instead. Okay. So this gives a very powerful result, and a sample of what you can do with this kind of machinery is to prove the following theorem that says if, let's say, X is a smooth affine threefold over an algebraically closed field of characteristic not 2, then you can enumerate rank 2 vector bundles on X in purely cohomology terms, and this is isomorphic to pick X cross Chow2 of X, right? Yeah, so this pick and this Chow2 are really examples of a cohomology set or cohomology groups that appears in the possible libs of the vector bundles, right? And this is, I guess, a theorem which doesn't have a proof, which is not in A1 homotopy theory. So it's kind of a good advertisement maybe for this subject. So it's natural to ask, what happens if we replace GLR, which classifies vector bundles, with other groups? Well, if I just look at this Morel and Asokwa event result, you'll see that the left-hand side is A1 invariant. If I take this cross A1, right, the value doesn't change because I've taken these maps in the A1 homotopy category. So the right-hand side, if this is an isomorphism, better be A1 invariant. But and that's true in the case of vector bundles. So A1 invariance of this right-hand side was established in this generality by Popescu, Lindell, and more generally is part of this thing called the Basque-Quillen conjecture. Okay, so in order to have access to sets in order to have access to sets via sets of interest in algebraic geometry via A1 homotopy theory, you must make sure that pre-sheaf of sets is A1 invariant to begin with. This is wildly false for many groups which are not GLR. So for G not GLR, this set H1 etale blank G do not exhibit A1 invariance in general. So let me just give let me just name drop. So Oyanguren and Oyanguren and Sridharan were really the first to come up with these counterexamples for PGLN. So this is a fact I learned from Ben, Antieau. And there's Parimala also gave counterexamples for ONs. So O3 and O4 in particular. And their examples, the X that they use is just a spec of the reals XY. So just A2 over the reals. Okay, so what I'm saying is that there are PGLN and ON torsors on this A2 over the reals, which are not extended from spec R. So in other words, these cohomology sets do not exhibit homotopy invariance. That's a thing. So fine, you can't really directly access the sets by A1 homotopy theory, but you can still ask what does XB at G compute? And as a first approximation to this problem, what does this compute? Also, second thing is to ask, like, how far is this from being an ISO? And as a first approximation to all these problems, you can ask, what is this? Pi 0 A1 B etale G. Okay. Right, so we already know, for example, that this is not the terminal sheaf in general. And so I because of lack of time, I won't be able to elaborate, but you just think about the case of B etale mu n. Let's say n is different from the characteristic of the field. Okay, so so these were the questions. These were the leading questions that we were asking before we even arrived at purity, and we could answer the last question, as it turns out. And let me write the theorem that we could prove. So theorem B. Okay, so so from now on, G and K are as above. Okay, then the sheaf. So the first assertion is that H1 etale G is in fact A1 invariant. Okay, so this is an escalation. So let me make a quick remark before. Okay, so firstly, this is curly H. I really emphasize that. So remark, this is an escalation of Parimala's observation. So of course, she didn't say it in these terms, but this is essentially what she proved using like hardcore, very explicit computation with matrices, that her counterexamples vanish Nisnevich locally. So in other words, so you have this funny torsors that she was looking at that witnesses counterexamples to homotopy invariance on Rxy. So what she showed is that you can find a Nisnevich neighborhood of a Nisnevich cover of A2xy such that these torsors actually trivialize. And this torsors being trivialized on a Nisnevich cover is not like a trivial thing, because these are like etale locally trivial torsors, right? But in fact, you can actually make them into constant torsors on a Nisnevich neighborhood. And an escalation of that, I mean, and what we should, this theorem B is just an escalation of that this A1 invariant phenomenon, this non-A1 invariant phenomenon does disappear once you Nisnevich sheafify this cohomology set. Okay. Okay, so then I'll write theorem C. Okay, so right, so I guess yeah, so EKW, KW. Okay, so theorem C is that in fact pi 0 A1 B etale G is indeed just this script H1 etale G. So there's a natural map B etale G, which is not A1 invariantized, into B etale G, which is A1 invariantized, just some localization, right? And it sheafifies to this isomorphism. Okay. And in particular, so here's a corollary. Right, so from the point of view of A1 homotopy theory, this next corollary is the most important, or something, is that pi 0 A1 B etale G satisfies Morel's conjecture. So Morel's conjecture posits that pi 0 A1 of any pre-sheaf is in fact A1 invariant. Right, so this is the Nisnevich sheafification of an A1 invariant pre-sheaf of sets. So there's no reason for it to retain its A1 invariant nature. But Morel was able to prove this if I replace 0 by like 1 and higher, like for the higher homotopy sheaves. But as we all know, pi 0 is always the hardest homotopy group or homotopy set. And he was not able to show that this pi 0 A1x is A1 invariant, except in some cases, like finite groups. And yeah, so this gives new cases of the validity of Morel's conjecture. Because we showed that this H1 etale is A1 invariant, and if you can show that this is in fact an iso, then of course this guy is also A1 invariant. Okay, so in the last 10 minutes or something, I can say something about a proof, but any questions about this?
How much of this requires the specific kind of sheaf B etale G, and how much would apply to sort of some random etale sheaf of spaces whose pi 0 happens to be, whose Motivic pi 0 happens to be A1 invariant?
Right. So here, so you're asking what is the axiomatics for this proof? Right.
Sure.
So this is exactly what I wanted to say. Okay. So, I mean, if you're in this like business industry or something, like if you want to prove some A1 invariant statement, most of the time you have to, you can't, it has to be some kind of axiomatics, right? So for example, in like this beautiful book by Mazar-Voivodsky, you prove this A1 invariance for like this this various sheaves with transfers via some axiomatics. I mean, the having transfers is like an axiomatics, right? And you say that many sheaves have transfers, so boom, there you go. So that's the kind of similar flavor, but because we are dealing with finite sets, the axiomatics is a bit different. and here's the axiomatics. So here's the key lemma. Oh, before I state the key lemma, let me write some. Let me just write some properties that a sheaf can have. So F is a functor from essentially smooth schemes, pre-sheaf on essentially smooth schemes over K into finite sets. Then we say that F is finitary if F of the inverse limit of a collection of smooth affine schemes is the same thing as the co-limit like this. So it's just continuous, if you want. So this is this is not an interesting axiomatic. This is commonly satisfied from any pre-sheaves, pointed sets. So here comes the interesting part. So we say that it satisfies Grothendieck Serre. So GS, if for any regular local ring R with fraction field K, f of R mapping to f of K has trivial kernel, right? This is a map of pointed sets. So trivial kernel means the inverse image over the base point is the base point. We say that he has strong Grothendieck Serre if in fact this map is injective, which is stronger than just having trivial kernel because these are not groups. And so the next terminology is I'm responsible for how bad it sounds, but Nisnevich Lexicif. If I convert the following elementary distinguished square, so you have spec A to spec B to spec A, and this is etale, and this is spec AF open, so F is inside A, spec BF, right? So what you can do is I can look at F of A mapping to F of AF, and I can look at the kernel in sheaf of in pointed sets, and I can look at the kernel of F of B mapping to F of BF. Right, so this is weaker than being a Nisnevich sheaf. Okay, so this is like the minimal, right? So if you're LA1 or L mode of something, then you take the and you have some exact sequence in if you're LA1 of something, this holds, for example.
Sorry, Elden,
Yes.
This map is surjective or something like that?
Sorry, absolutely, yeah. Yeah. Does B to A have to have Nisnevich lifting property? Well, no. Well, mutually, spec B and spec AF has the Nisnevich lifting property, right? So this is just an elementary distinguished square. So I guess I know what Chuck means. So yes, this is the answer. So you have, of course, on the closed complement, you need this to be an iso, right? Yeah. So it's an elementary distinguished square. Okay, that's what you need. Okay, so let me write the key lemma now. So F is a functor from essentially smooth schemes up into pointed sets. Okay. Finitary. So 1, if F is Nisnevich excisive, then f of x mapping to a-ness of f of x is surjective for all x in dimension x less than equals to 1. Okay, so you can sort of prove a little bit, you can prove some surjectivity statement for DVRs. And for us, the most important x is just a1 over L over a finitely generated extension of the base field. And if F has strong Grothendieck Serre and the Nisnevich sheafification of L is isomorphic to the, so the Nisnevich sheafification of F evaluated at L versus the Nisnevich sheafification of F evaluated at L times A1. So this is very, very weak homotopy invariance, right? So Parimal's counterexample is A2. Yeah? So that's not, it doesn't dismiss this kind of thing. Right? And in fact, you can prove that in many cases, A1 invariance just over a field is okay. Then A-ness of F is A1 invariant. Yeah, so this is the axiomatics that leads to proving that something like H1 etale is an A1 invariant sheaf. Okay. Right. So I guess I won't have time to talk about this, but shadows of this kind of axiomatics is found in work of Utsav-Chaudhuri, where he verified Morel's conjecture for H spaces, and also shadows of this. The idea of using Grothendieck Serre type property to talk about A1 homotopy invariance was in the third paper of Asok, Cueva, and Vent. So this is sort of a combination of these two papers, basically. So maybe I'll finish off the talk by writing as a last by proving theorem A given all this theorem A theorems B and C. So the master diagram, if you want to understand purity, is like this. So you have H1 etale xg mapping to the sheafified version, mapping to xb etale g a1, mapping to pi 0 a1 b etale g evaluated at x. So by the theorems, this is an iso. And now you can show that this is surjective if and only if purity holds. This is from the fact that you can rephrase purity. You can rephrase purity in the presence of local purity in terms of Morel's unramified sheaf technology. So yeah, so if this was surjective, then you can show that this must be surjective. And that's how you. I mean, this master diagram governs. Well, it's what we think governs this purity conjecture of Colliot-Thélène and Sansuc. Okay, I'm over time. Thank you.
Okay, thanks a lot, Elden, for an interesting talk. So let's all give it up for Elden. And we can have some questions. Please go ahead.
Elden, I had one question about the axiomatics.
Yes.
I was kind of curious if you have something to say more generally about some axiomatics that would hold for an etale sheaf of spaces, not just for the set, but which would guarantee that when you do this sort of Nisnevich sheafification of pi 0, that it satisfies Morel's conjecture.
So at the moment we don't. So the way that we prove this part 2, for example, really requires you to go deep into Elnis, LA1, Elnis, LA1. Like you really need to understand, you really need this construction, and you need to make some very point set level arguments, which seems to be quite difficult if you perform it on the level of spaces, but maybe not impossible. So I guess at the moment we don't. Right.
Okay, any other questions?
I had one more. It's okay. So what, do you have a sense of where the first Postnikov obstructions will appear, and in what sorts of cohomology groups?
Absolutely, yeah. So I can say something quickly about this, right? Yeah. So let's say you wanna compute with something like pi. So you need to understand pi JA1 B etale PGL n. Let's say, like you need to understand this. So pi 1 A1, as you probably can guess. So there is an obvious replacement for GM, is just twisted alpha twisted K theory in this.
You mean where you base point at an Azumai algebra whose Brouwer class is alpha?
Exactly. Right. So yeah. So the way you access this, right? So the way you access this is to use the following fiber sequence, which is an A1 fiber sequence. So you take B etale PGLN, you map to B2 etale mu n. So you've chosen some base points, so you determine an Azumai algebra. Sorry, you've chosen an Azumai algebra, so you've determined a Brouwer class, right? So you can take the inverse image, and you can take the fiber, and it's just B nis GLN SLN, sorry. Right, so there's the kind of computations you can make, and you see that pi 1 is this kind of like twisted K1, and pi 2 is a combination of mu n and some Milnor-Witt groups. And beyond that, you're in some very, very unstable range. That's very scary. But we were hoping that using just these two things and some knowledge about how these things look, cohomology, how these things look like, and can lead to counterexamples.
So I guess Colliot-Thélène and Sansuc basically prove that the first obstruction always vanishes for regular surfaces.
Right. So you can reprove this Colliot-Thélène and Sansuc by just seeing that the first obstruction really lives in H3, right? So if your A1 homotopy dimension 3, like a smooth affine scheme over a field.
Sorry, doesn't it live in H2? I mean, the first one will be from like.
Yeah, right.
H2 of pi 1.
H2 pi 1. Right. Sorry, I apologize. Yeah, H2 pi 1. So your A1 homotopy dimension 1. you can do that, but you should expect that H2 pi 1 the obstruction in H2 pi 1 to disappear, I guess, right? I mean, if you are untwisted, this is just GM, right? And H2 pi 1 this GM is just 0. So if you can prove, I mean, you should expect that to vanish as well. So you can reprove Colliot-Thélène and Sansuc in slightly more flexibility where your dimension is a one homotopy dimension and not full dimension. So yeah, like Joannou divises over P2 or something like this. Yeah.
I mean, you know, it'd be great if there was an H3 obstruction, because we don't know if purity fails for dimension 3. So that would be, or 3 or 4 or 5. So that would be fun.
Yes. Well, yeah. So we set ourselves some deadline to see if we can come up with something like this. If not, we'll just release this in this form. Yeah.
Okay, any more questions? I think that's all for today. So let's thank Elden again for an interesting talk. Thank you.